start with some pretty pictures.
Researching ignorance of the one, like, I'll put that stuff. There's lots of
We're going to talk today about initiation of motion with flowing water, because that's where we're at. There's different sorts of flowing water. This is a pretty full river, Ellis River in Maine. One of those really few places I've ever been, maybe the only place I've ever been where during essentially flood flow, the water is clear. I mean, it's brown, but it's just stained brown. It's actually still clear. Contrast that with something like this, which is up in Alaska. A stream that's cutting through a dam formed by a lateral moraine of a glacier that you can see the ice from. Here's another favorite stream of mine, the Paria River in, I think this is still in southern Utah. Muddy water is what Paria means, and it is. So we've got flowing water. We're going to talk about ways to figure out whether something's moving. So let me back up then. The fundamental question, and this is kind of a fundamental question of surface processes, given a particular sediment grain, does it go or does it not go? We're going to look at this question of if I've got my geomorphic agent here, that is the flow, and I've got some stream bed with grains in it. In particular, say, one particular grain might be trying to resist the forces of our geomorphic agent. Does the flow apply a force sufficient to actually move that particle? Now, if we can answer this question, can that flow move that particle? We can also answer the inverse question, that is, if given that a particle did or didn't move, how big or small must the flow have been? And this is a technique used in paleoflow reconstruction, for example, Missoula flood. If we know, for example, that particular grains were deposited by the flow, then we know approximately what that flow must have been, because the flow must have moved the particles there, yet it was at that stage where it was just big enough to move them there, but not to take them away from there, if you know what I mean. So, we can also, well, when I say how big or small must the flow have been, though, that does kind of force us to address this question of what is big or small. Are we talking depth, velocity, discharge? I mean, kind of, yeah, all of that. So we'll have to deal with all of those kinds of things. Now there are other important questions like how much moves and of what sizes. We're going to stick for now with the go, no-go, because that's something that we can make some reasonably good progress on, and even learned some other stuff about fluvial mechanics in general along the way. Okay. So, in order to answer this go, no-go question, we generally use, well, let me first say, we could try to do a force balance here, and that can be somewhat instructive, trying to figure out the drag force and the lift force on some particle like this. But when it comes down to it, we're just going to use a graph called the modified Shields diagram. The modified Shields diagram was developed from flume data, and it plots dimensionless shear stress versus essentially a dimensionless particle size, particle diameter. So we'll need to deal with that. This one here is known as the Shields number. And we'll have to become familiar with that. This one is known as the, well, there's not a one single standard that people use in their modified Shields diagrams, but in general, well, they're all pretty similar. The one we'll use, we'll just call it a particle Reynolds number. Why not just Reynolds number? Well, the Reynolds, there are all sorts of flavors of Reynolds number. Probably towards the end, maybe today, we'll get to like, well, what's the sort of plain vanilla Reynolds number? And what's that all about? Yeah.
Is that like B sizes and stuff?
No, not exactly. Okay. So the Shields diagram just looks something like this, and I'll go to something on the screen shortly, but we've got our Shields number on this axis. We've got our particle Reynolds number. On this axis, and essentially it's a curve that looks something like that. These are both log axes, and if the Shields number is greater than this critical value, so this will use a symbol tau star. This will use this fancy RE sub P. Not sure where we get the fancy R, but it's just something that we do. And this critical value will give it a tau star stub C for critical. And the idea is that if the Shields number is greater than this critical value, then we've got go. And if it's not, we've got no go. Okay. Let's go to some slides. This is a modified Shields diagram. And so here we see this is labeled tau c star because there's only the one thing graphed on it. Well, sort of. And here labeled RE sub p for particle Reynolds number. The different sectors of the graph labeled go and no go. And the indications here of at least rough size ranges for particles. That is, way down here we've got silt sized particles, and here we've got sand sizes, and here and up we've got gravel and larger sized particles. Now, so far, this is going to be a bit perhaps mysterious because I haven't yet defined exactly how we get either of these dimensionless numbers. I'll get there. Just want to show you what we're dealing with first. So this is a functional fit that somebody's made to data. This was Shield's original curve or diagram. And boy, if you're really spiffy, you can decipher what this actually says here, because it does actually give us something, the formula for the Shield's number and his particle or roughness Reynolds number here. A couple of points to this graph. One is he's already sketched that the data describe a fuzzy band, not a bright line. And he's combined several experiments to plot on here. The other thing is that this is the original and nobody uses it because it's really darn inconvenient. Because it essentially has shear stress on both axes, and that means that's hard. So that's why everybody uses a modified Shield's diagram. Here is a modified Shield's diagram with more data on it from 29 different data sets. And here is where if you didn't have the idea before that we're dealing with something of a fuzzy curve or fuzzy criterion rather than a really bright, sharp line, this should drive it home. I've marked on both of these where so this is the range here of sort of the fuzzy band of Shield's data. This is the value on the previous graph that I showed you, where the line is. I'll just go back quickly to that, right? So this value asymptotes to about 0.03, and that's 0.03 right there. And that's 0.03. So based on all these data, what it appears that we're doing is defining our criterion near the lower limit of this cloud of data. And the thing to remember about these is this is all people staring at grains on the bed of a flume and deciding whether they're moving or not. So it's it's almost a question of, well, how long did you wait to see? All right. If we look then at actual transport rate measurements in both flumes and real streams, and what we see here are measurements from Oak Creek. Yes, that's the Oak Creek that goes through campus, but measured up at the McDonald Forest. This thing in Israel, Emerald Stream in Israel, and then various flume data. and we look at that 0.03 value of the shield number that for gravel, that is the value that it asymptotes to. That value is right about here, right there. And you can see that almost all of the Oak Creek data are transport rates measured at values of the shield's number smaller than the so-called critical value for initiation of motion. So what we seem to really see is that the shield's criterion kind of separates as a part of the graph where our transport rate is increasing something like the 11th power of our shield's number versus a part of the graph where it's more like shield's number to the 1.5. So it's if I'm dealing with transport rates that are up here, it's a decent enough approximation to use that as a threshold. But if I'm actually wanting to measure marginal transport rates, then it's the idea of that bright line threshold is kind of bogus. Now that's why engineering manuals are more going to graphs like this that say, okay, this is more about the probability that something's going to move. So this is from a stream restoration design manual, and here we've got the so-called critical value of shear stress. This is dimensional divided by the actual shear stress. So that's saying, well, this is the probability, oh goodness, I think it's the probability that it doesn't move. It needs to be, let's see, because it's saying, okay, yeah, if the critical value is twice the shear stress, then there's like a 95% chance that it won't move. Whereas if I'm down here where the critical value is less than the shear stress, then there's a decent chance of motion. And this is the sort of, the other sorts of things that we find in that manual are, okay, so here's how you size your riprap at your, if you want to protect these banks or this bed or whatnot. Use a factor, make it big, and then it won't move. So, just to say, okay, if we were actually going to use this for these sorts of purposes, that's the kind of thing we'd need to consider. Probably most of us aren't going to be designing that sort of thing, but you never know. Okay. So I've shown the diagram. What's actually on those axes? I know you're just like going, okay, great. I've got this graph with this funny curve on it. What the heck is on that? What is this so-called Shield's number that it's a dimensionless shear stress? What's this so-called particle representation? Let's go back over here then and answer that basic question. So, remember on the y-axis, we have our Shield's number. And this is a dimensionless shear stress. So, Shield's number, we use tau star. If you look in the literature, there seem to be a few different common symbols that people use. Tau star is a good one because it does harken back to the common use of tau as a symbol for shear stress. All right, so the Shield's number is, in a nutshell, it's the bed shear stress divided by the unit buoyant weight of the particle. So, you know, the idea being that, well, if I do an experiment with, say, ground up coal, or I do an experiment with a different fluid even, like oil or glycerin, or I do something on Mars, I can still calculate numbers that are then comparable to other numbers on that graph. So that bed shear stress good old tau, and I've given it a 0 to indicate that we're talking at 0 height above the bed. So we're talking bed shear stress. And down here, what did I say? Unit buoyant weight of particle. That means, so the way that comes out is I've got grain density minus water density or fluid density. Here the W indicating typically we're dealing with water. And then gravity and grain diameter. And that's just how that's defined. There's nothing really more profound I can say about it, except to see how we can maybe make it a little bit simpler. So let's get something a bit simpler, shall we? All right, first thing we'll do is get rid of this bit in parentheses. We'll define something that is the relative submerged specific density, or maybe gravity, whatever. This is dimensionless now. You start to get the idea that people who do fluid mechanics and sediment transport and whatnot really like to make everything dimensionless. So with that, I can go ahead and rewrite this as which isn't necessarily objectively simpler, but at least I got rid of something in parentheses. All right. In order to make it simpler still, oh, you know what though? Always a good idea to check our units. Let's just make sure this is indeed unitless. So, let's see, kilogram meters per second squared per length squared. Density and mass down here, volume there. Gravity, length per time squared, and length. Okay, I got t squareds cancel. L to the fourth, so all my L's cancel, my mass cancels. Yes, indeed, it is dimensionless, if you were in any doubt. Okay. So notice what we've got here. We've got a characterization of the flow, at least according to the shear stress that it's generating. We've got the fluid in density of the water, and we've got grain characteristics in the diameter and the relative submerged specific density. And we've got planetary characteristics in gravity. So let's talk about then how do we get a bed shear stress. We're going to make an approximation or assumption. We'll start writing what I'm saying instead of what I mean to write. So, what's for uniform steady flow? Uniform flow means that my width, depth, and velocity are constant along stream, and steady means that those same flow parameters are constant in time, or at least slowly varying enough that we can assume that time derivatives in various equations go to 0. What this lets us do is draw us a familiar sort of idealization where we're looking at a hunk of water on an inclined slope. It has, that hunk of water has a thickness h. It has density rho w. And we can go ahead and draw axes z and x. Now,
I have a quick question.
yes.
Is this talking about water flowing over, I guess, just sediment down a hill, or are we talking like rivers and streams?
Yes.
All of the above?
Yeah.
Okay.
All of the above. Now, I hope that I don't need to go through this again, because this is going to be, we're going to use the same formula for shear stress that we use for glaciers, that we use for landsliding. That is that my bed shear stress here is just density of water times the thickness of the hunk of water, gravity, and go ahead and sine of the slope angle. We're going to do a couple of things then. Stream bed slope angles are almost always pretty small. So my small theta lets me get away with a couple of things. First of all, sine theta approximately equal to tan theta, which is minus dz dx if z is the bed elevation, which we'll essentially define as a capital S. We've kind of done that before. Second is that cosine theta is approximately equal to 1, and therefore I don't need to worry so much about whether that's a bed normal depth or a vertical depth, because if cosine theta is about 1, then h over cosine theta is approximately equal to h. That is, if this is the bed normal depth, then dividing by cosine theta is the vertical. And typically with streams, we're just not going to worry about the difference between those two. If we're dealing with a 40-degree slope, hill slope or something, then yeah, we got to worry about the difference between the bed normal and the vertical. When we're dealing with a stream, that a steep stream is like 2 or 3% slope, and difference between vertical and bed normal, even if you could actually see the difference on the ground, is not significant for us. So these two things allow us to take this and say, well, we've got approximately rho, the density times the depth times gravity times slope. That's a lousy S, so I'll draw it one more time. Now, that's all very nice, you say. So what? Well, getting there. Okay to erase this? So, that lets us come up with a much more convenient, easy to remember, and easy to use Shields number. So if my tau star is tau 0 over rho W R G D, my tau is rho W H G S, tau star rho's cancel, gravity cancels. We're into planetary independence now. These little things make me excited. There we go. So, just the depth times the slope divided by this relative submerged specific density and the grain diameter. This one, we will use a number for quartz so frequently that it's kind of startling when we use something different. So what's the density of quartz? Anybody know? 2.67, is it? 2.65 grams per cubic centimeter. So go back to this. 2.65 over 1 is 2.65 minus 1 is 1.65. So R is typically 1.65 obviously if we're dealing with nice, hard crystalline, no bubbles in it basalt, then we'd have to use something like more like 2.3. Okay? All right. Now, on my other axis of my Shields diagram then, I had something that I said was like a dimensionless grain size. And I called it a particle Reynolds number. All right. Another not so profound or invested with meaning expression, that is, you just gotta use it, it's just what people use or something very, very much like it. It just happens to have dimensions that cancel out and has grain properties, fluid properties, planet properties. Okay, so diameter twice. This our relative submerged specific density, our gravity, and our kinematic viscosity. And for water, that's going to be typically 10 to the minus 6 meters squared per second. As long as we're not dealing with really, really like sub-zero cold water, viscosity is not going to change a whole lot. Okay. This part's a bit anticlimactic. I don't really have anything interesting to say about it. It's just a thing. So, how good? Okay, if we're going to use this thing, this Shields diagram, I said it's kind of fuzzy, but so maybe we can get away with some slop here and there. I've already thrown in some approximations. It's worth asking, okay, well, just how good is this uniform steady flow hunk of water type approximation? Because it seems a little odd that we can just treat water like it's a big hunk of earth. So that's a decent question if you had it. And it's probably worth addressing. It also lets me talk about some other characteristics of flow. In answering the question of how good is it, we actually even get to how do you measure discharge in a stream at all. So, what did we say maybe at some point about the rheology of water? It's a linear fluid. What's rheology? Start there. Well, rheology is essentially that relationship between shear stress and strain rate. Strain rate, in this case, I'm going to write like so. Put a bar over the U, because I'm assuming that we're dealing with turbulent flow. And if I'm dealing with turbulent flow, then the instantaneous velocity is, like, by definition, fluctuating all over the place. And that's actually it affects fundamentally the way the fluid behaves. So the bar there indicates a time average velocity. And for my proportionality, whereas for regular old viscous flow, I'd put in a viscosity here. I'd have my fluid density, and I'd have my mu or whatever. I'd have a viscosity there, I think mu. In this case, I'm going to throw in a Kluge number. And this is called turbulent eddy viscosity. What's up with that then? If my flow is turbulent, and I've got these turbulent eddies of varying sizes, smaller near the bed, potentially larger, at least the largest of them, potentially larger as I get up into the water column. And in general, I know that the velocity goes to 0 near the bed, and it's probably going to be a maximum up here then. And if I'm doing all this swirly stuff, then I'm constantly or continually moving water from high velocity regions to lower velocity regions and vice versa. So I'm continually taking something that's slow, having to accelerate it, putting something that's fast, and having the other thing kind of get a little boost. And what that effectively does is make the fluid act like it's more viscous than that molecular viscosity. So now it's not a viscosity you're going to be able to feel with your hand, because once you sort of dip your hand in it and pull out a cup of it, it's no longer, we're talking about macro scale effects of these turbulent eddies rather than the sorts of things you can feel with your finger. So that's one thing. This turbulent eddy viscosity then is a bit of a funny character because as I've drawn here, it's going to depend on the sizes of these eddies. It's going to be smaller near the bed, larger farther from the bed. So it's going to, well, I'm just going to write something. I'm going to say that my turbulent eddy viscosity increases with height above the bed. And this thing is defined, I'm going to define as a so-called shear velocity. This has this combination of shear stress and density has units of velocity. We call that the shear velocity. It is not an actual velocity of anything except by coincidence. It simply is a way to express the shear stress of water as with units of velocity. This here is von Karman's constant. And it equals 0.4. Well, so what? Well, if I plug that into that, and I'll spare you the math, I come up with an expression for the velocity as a function of height above the bed that looks like so, like this. Z0 is simply the velocity, the height where the velocity goes to 0. Z is height above the bed. U star, shear velocity, which is related to the shear stress, von Karman's constant.
What is the LM looking thing? The LU? L mu?
Oh, log, natural log. I get so used to the way I do that. I believe I have time, yes I do, to show you, okay, that's wonderful, Lancaster, so they BFD, right? And I mean, does it work? A, does it work? And B, so what? Well, here's the does it work part. These are data collected by students at a side channel in the Middle Fork Willamette River, I think 2011. And this is, we're plotting time average flow velocity versus adjusted height above the bed. And you might notice that we've got a log axis on the horizontal, a linear axis on the vertical, and we fit a straight line to it, which is a logarithmic function, and we have an R squared of 98%. So yes, it works. The total depth here, let's see, total height, I think here, we did have to leave off a couple of data points at the top because of wind and surface roughness, turbulent, or sort of wave roughness. But that's at about half a meter. Now, so real velocities do follow this log profile, which is why it's known as a law. and it's called the law of the wall. And so the how good was that? So from this constant here, I can figure out what my shear velocity is and therefore what my shear stress is. And I will tell you without writing it that it's 12.5 pascals. Now, I've also had students survey the water surface, and from that come up with this slope, at least for this part, of 2.28 times 10 to the minus 3. This is where those velocity data were collected, where the depth is 0.53 meters. So if I use that tau equals density times gravity times depth times slope, I come up with a shear stress of 11.8 pascals. 11.8 versus 12.5 is not perfect, but it's okay. Considering how fuzzy everything is and how difficult it is to measure a good water surface slope that small, you know, it's probably pretty decent. Yeah, I think that was about that. So, you might also want to know, well, when do I use this turbulent viscosity thing? And I would say, short answer, I would say, oh, trust me, it's always turbulent. Long answer is, all right, you really want to use the vanilla Reynolds number. Reynolds number is the average velocity over whatever you're looking at, depth in this case, the depth, the flow depth, the kinematic viscosity. If I plug in, if I use this, the fit that I got there, I come up with an average velocity of about 0.47 or half a meter per second. Depth is about half a meter, and this is 10 to the minus 6. So I come up with about 2.5 times 10 to the 5th for this number. And turbulent is when the vanilla Reynolds number is greater than 2,000. It's always turbulent. Like I said, for this particular case, I came up with 2.5 times 10 to the 5th for my actual Reynolds number. Quite a bit greater than 2,000. Almost any flow you ever see on the surface of the earth is going to be turbulent. Of water. Not of oil, but of water. All right. That's that. I know that was a blast. I went through that all real fast, but we'll take a breath next time.